Hydro-Acoustic Resonant Propulsion, H.A.R.P, a nanotech-enabled atmospheric sonoluminescent drive system. Abstract. We propose a novel propulsion technology termed Hydro-Acoustic Resonant Propulsion, H.A.R.P, which utilizes multi-bubble sonoluminescence triggered in airborne water vapor to generate directed thrust. This system replaces conventional combustion or rotor-based thrust mechanisms with a matrix of nanotech-enhanced acoustic transducers capable of creating localized cavitation events in atmospheric microdroplets. The collapses of these bubbles produce micro-shockwaves, which, when coherently directed, generate sufficient net force for aerial propulsion and maneuvering. This approach offers a fuel-less, low-noise and highly scalable propulsion alternative for UAVs, stealth vehicles, and high-atmospheric drones. Introduction. Sonoluminescence, first observed in the early 1930s, is the emission of short bursts of light from imploding bubbles in a liquid when excited by intense sound fields. Over the years, it has been the subject of extensive experimental research due to the extreme temperatures and pressures generated during the bubble collapse. At the core of this phenomenon lies the ability of acoustic energy to compress a gas cavity to such an extent that it emits a flash of light, suggesting plasma-level energy densities. Historically, sonoluminescence was confined to controlled laboratory environments, particularly within single-bubble systems. However, multi-bubble sonoluminescence (MBSL), involving a cloud of collapsing bubbles, has been observed to produce localized zones of intense energy release, albeit with less uniformity than single-bubble systems. This paper proposes that under specific atmospheric conditions, particularly in regions of high ambient humidity, it is feasible to induce MBSL in airborne water vapor using advanced nano-engineered acoustic emitter arrays. We believe this marks a significant breakthrough in the conversion of ambient atmospheric matter into mechanical force, a step toward non-chemical field-based propulsion. Scientific foundations: sonoluminescence. Mechanism. Sonoluminescence occurs when an acoustic wave causes a microscopic gas bubble in a liquid to oscillate and collapse violently. The resulting implosion compresses the gas within the bubble, leading to adiabatic heating. This heating is believed to cause temperatures exceeding 10,000 Kelvin and pressures of several thousand atmospheres. The emission of light, though not fully understood, is thought to stem from ionization of gases within the bubble and subsequent plasma formation. Biological examples. Remarkably, some marine species naturally produce cavitation and sonoluminescent effects. The pistol shrimp, Alphiidae, snaps its claw to create a high-speed water jet, forming a cavitation bubble that collapses to emit a visible flash and stunning shockwave. The temperature inside the bubble can exceed 5,000 Kelvin, with pressures surpassing 80 atmospheres, enough to temporarily ionize the surrounding water and knock out or kill small prey. Similarly, the mantis shrimp, Stomatopoda, uses its raptorial appendages to generate powerful strikes, reaching speeds over 20 meters per second. The resulting cavitation bubbles collapse with sufficient force to generate localized heat spikes above 8,000 Kelvin and shock waves that can fracture glass or break aquarium walls. These creatures demonstrate nature's high-efficiency acoustic-to-mechanical energy conversion, the same physical principles that H.A.R.P is designed to replicate in the air. Multi-bubble cavitation in airborne droplets. Atmospheric humidity consists of suspended microdroplets, especially in fog, mist and tropical environments. Estimates suggest a density of 10 to the 7 to 10 to the 9th microdroplets per cubic meter in high humidity conditions. By deploying focused gigahertz range acoustic waves, it is theoretically possible to induce cavitation in these aerosol droplets. Rapid pressure oscillations coordinated through phase-controlled emitter arrays would allow targeted collapse events, similar to MBSL observed in liquids. Energy dynamics. Each cavitation event, though small, produces a localized micro-shockwave. When synchronized across a wide emitter surface, the cumulative effect becomes significant. Assuming synchronized bubble collapse within a cubic meter, energy conversion on the order of 1 to 10 joules per cycle could be achieved, resulting in directional momentum transfer. These values increase non-linearly with vapor density and emitter resolution. System performance model, lab-scale projections. Initial small-scale prototypes have demonstrated measurable force generation in controlled fog chambers. With optimized emitter density and humidity levels above 90%, thrust-to-weight ratios of 0.1 to 0.3 Newton per kilogram are achievable. Atmospheric dependency. Performance scales with ambient moisture availability. In lower humidity zones, the system may employ auxiliary vapor generation systems or hydrophilic surface condensation to increase local droplet density. Acoustic signature. Operating in the ultrasonic to hypersonic range, the H.A.R.P system remains effectively silent to human perception. This provides inherent stealth capabilities, reducing both audible and thermal signatures compared to combustion-based platforms. Scalability and application envelopes. The architecture is modular, allowing emitter density and system scale to be adjusted for nanodrones, UAVs, or larger VTOL craft. Future concepts may include variable frequency adaptive systems for high altitude or planetary atmospheric applications. Applications and implications. Reconnaissance and ISR, ultra-quiet, persistent surveillance platforms in urban or denied environments. Covert operations, silent insertion, extraction of lightweight payloads or autonomous craft. Climate exploration, long-duration, high-altitude probes for weather or environmental monitoring. Non-lethal acoustic systems, repurposing for crowd control or targeted EMP-style burst effects. Energy harvesting UAVs, self-sustaining drones powered by atmospheric energy cycling. Development Roadmap Phase 1. Construct lab-based vapor chamber. Demonstrate bubble collapse and light emission in high-density aerosol. Benchmark energy conversion metrics. Phase 2. Build nano-emitter array prototype. Integrate with hover-capable test rig. Validate thrust vectoring under controlled atmospheric conditions. Phase 3. Full-scale UAV prototype. Field testing in varying humidity zones. Integrate vapor condensation module. Phase 4. Multi-craft swarm simulations. Advanced signal steering via AI acoustic mapping. Funding requirements and technical team. Breakdown: nanofabrication equipment and clean room access, high-frequency control electronics, custom fog chamber and cavitation diagnostics, interdisciplinary team, physics, fluid dynamics, acoustics, nanoengineering. Conclusion: Hydro-Acoustic Resonant Propulsion represents a foundational shift in propulsion theory. By transforming ambient water vapor into a reactive medium via acoustic manipulation, H.A.R.P eliminates the dependency on fuel, combustion, and mechanical rotors. It draws inspiration from nature's own high-energy strategies, as demonstrated by marine life, and scales them into a coherent system for future aerospace deployment. With targeted investment, H.A.R.P could represent the next generation of low-signature, fuel-independent aerial mobility.